Okay, bom dia or good morning. This is the second class of fundamentals of the vitreous or glassy state. We will be continuing to talk about viscosity. Viscosity is so important that we have to continue a little bit more because, as we have discussed last week, viscosity is likely the most important property of glasses. Viscosity controls almost everything. All the transport processes, or most of the transport processes in glasses, including relaxation, glass transition, viscous flow, diffusion, crystal nucleation, crystal growth, fining, the elimination of bubbles, melting, homogenization controlled by viscosity. So we have seen briefly this very important plot that will be discussed several other times, the enthalpy versus temperature plot. I'll be coming back to this plot several other times along this next few weeks. Okay, let me go quickly to some of these slides. One key feature of viscosity is the fact that for glass-forming materials, for glass-forming substances, it varies from 10 to minus 1 to 10 to the 14 Pascal second in the range where most properties are measured. And a key feature of this wide variation of viscosity is that it allows us to shape glass products, bottles, tubes, fibers. Different shapes are possible due to the wide variation of viscosity. We also discussed why there is no data in the intermediate range, because some glasses or some glass-forming materials crystallize so fast that one cannot measure viscosity in some ranges. Due to this fact, it's really important to have good equations to fit data from the low viscosity to the very high viscosity end. We need some equation to be able to interpolate and properly fit this kind of data. And this is one topic that I'm going to discuss next. Which equation best describes the viscosity of glass-forming melts? So we have seen the definition of viscosity, the various ranges of viscosity where one can melt a glass or shape a glass or anneal a glass. So I'm going very quickly through these slides, and then very quickly again going to this one. Viscosity equations, which are useful to fit or to describe the viscosity of glass-forming melts. We have seen the Vogel-Fulcher-Thurman-Hesse equation. It's an empirical equation derived in the early 20s, which still is very much used to describe the viscosity of glasses. Then we have the Adam-Gibbs equation. I'm going to go in more detail through this equation. The Avramov-Milchev, the Miega or Miega equation. If you see here in chronological order these different equations, and there are 10 other equations or so to describe the viscosity of glasses, have been derived by different people. If we look in this form, A1 plus B1 divided by T minus C1, they don't make much sense. But if I rewrite some of these equations in other forms, and you can refer to this reference number 18 in the book chapter that I have given to you. In this reference 18, the details on how you can go from this form of equation to this form here. These are the same, Vogel-Fulcher-Tillman, or from the Avramov-Milchev in this particular form to this form here and so on. The details are described here. But the key point in doing so is that we can now see the physical meaning of these constants. For instance, what's A1, A2, A3, and A4? This is the value of viscosity at very high temperatures. If we extrapolate the viscosity curve to extremely high temperatures, this is called the eta infinity, the value of viscosity at very high temperatures, where we have a gas, no longer a liquid, but we have a gas. And this is eta infinity. So all these constants here, A1, 2, 3, 4, refer to that value. Also, let's take a look in the Vogel-Fulcher equation. B1 is like the equivalent of an activation energy. It's the equivalent because it's not divided only by T, it's divided by T minus C1. So it's related to the activation energy for viscous flow. In C1, best known as T0, you find this equation in the literature like A plus B divided by T minus T0. T0 is the temperature where the viscosity tends to infinity if this equation applies. So this is the meaning of C1 and T0. When the temperature, the actual sample temperature, tends to T0, the viscosity tends to infinity. I'm not saying that this happens, but this is the prediction of that particular equation. These other two equations here do not predict a divergent viscosity. Anyway, so if we rewrite this equation here in this particular form, you see that eta infinity is the value at very high temperatures. Tg is the glass transition temperature of the glass. And to normalize this temperature for different heating rates, cooling rates, etc., the value of 12 is used. The log of viscosity is 12. So this is the meaning of this 12 here. It's the log of viscosity at Tg. And then a third parameter, m. M is the fragility of the liquid. M is the derivative of the viscosity at Tg. I'm going to show some slides in a minute or so. So for the time being, just be aware that there are three parameters: the fragility, eta infinity, and Tg. So it's much better to read that same equation in this way, because now we can relate A1, B1, and C1 to physical parameters, which have a meaning: fragility, eta infinity, and Tg. And the same can be done for all these equations. So the Avramov equation is written in this form. Again, eta infinity, Tg, and m. So there are 3 parameter equations. We cannot, in general, predict the values of these constants. So we normally fit one of these equations to viscosity data and get the values of these parameters. Although, I must tell you, we are lucky because eta infinity does not vary much from glass to glass. People have fitted these equations to many, many glasses, 500 different glasses, and the values of eta infinity are within a very narrow range. Normally, this value is from -2 in log to about -5 or so. So this is one parameter which you can take an average like -3 or so, or -3.5, and then you are left with only 2 fitting parameters, m and Tg. Of course, you can also measure Tg independently, and then you have Tg. If you can measure by DSC, for instance, so you're left with only one unknown parameter, m. So I gave you some homework to do. We are going to discuss this after the class. I hope you're able to fit some of these viscosity curves to the glass that you have adopted. Each student has adopted a different glass. They are going to work with the same glass throughout this course. But I'm interested in knowing what sort of values of eta infinity have you gotten from your fits. They have to be within this range here. -2, -5 in Pascal second, when the viscosity is written in terms of Pascal second. Most fits give values in this range here. So, okay, viscosity equations then. We are talking about viscosity equations, and one of the most important viscosity equations is the so-called Adam-Gibbs equation. This equation has been derived in 1965. It has more than 4,000 citations. It's one of the most important papers published in the glass field in general, in all sub-areas of glass. And the key idea is that it connects a kinetic property, viscosity, to a thermodynamic property of the system, the entropy. So these researchers were able to connect a dynamic property with a thermodynamic property. And this is the importance of the Adam-Gibbs equation, is the value of eta infinity, this guy here, eta infinity, exponential of a certain constant A, and A is related to the free energy barrier for viscous flow. Free energy barrier. T is the temperature, and SC is the configurational entropy of the liquid, which can be calculated independently. If you have calorimetric data, CP data, you can calculate independently the entropy, and then eta infinity, you can guess some value in this range here, so you're left with only one unknown parameter, A. Another interesting feature of this theory, or this model, is that Adam-Gibbs, they derived this equation assuming that different cooperatively rearranging regions, CRR, exist in the liquid. What's the meaning of CRR? Think of a traffic jam. If you are here in São Carlos, in the neighborhood of the Federal University, where we are at, daytime, there'll be a few cars running, and they move independently, Think that one car is a sort of structural unity, a few SiO4 tetrahedra, if we have a silicate glass. They move independently. Now, if you come at rush hour, they no longer move independently. There is a traffic jam, and your car's velocity will be limited by the car in front of you. And the car in front of you will be limited by the velocity of the other car in front of that. So there are groups of cars that can move at the same velocity together, because they're coupled. This is a cooperatively rearranging regions. So think of a glass forming melt of some single unities, some double unities, and some unities with 20 of these tetrahedra. They are cooperatively rearranging regions. And when we cool down the liquid, they become larger and larger. It's the same thing in the traffic. If you are only a few cars, they are well apart from each other, they move independently. The more cars you have, the closer they are, the larger are these cooperatively rearranging regions. This is the idea, very nice idea, it makes sense. And based on this idea, the entropy, that's where the entropy enters. You can calculate the entropy, the number of possible configurations for a given free energy. And that's why the entropy is related to the viscosity. So CRRs are defined as the smallest structural elements or molecular groups in the glass or in the liquid that can relax or move to new configurations independently of their environment. These groupings, they relax independently. And there is a distribution of these groups. And they tend to become larger and larger as the viscosity increases or as the temperature decreases. And this is predicted by this equation, the Adam-Gibbs equation. The main problem is to calculate the configuration entropy for a very complex glass-forming liquid. If you come up with an equation to calculate this, then you have a perfect viscosity equation. And this is what the Maega guys did. This equation, Miega or Maega, derives from a model for the entropy. These authors, 5 authors, came up with a model for the entropy. They calculated the entropy, inserted in the Adam-Gibbs equation, and then resulted in this expression here. This is the Adam-Gibbs equation with a certain expression for the configuration entropy. In the Avramov-Milchev is a little bit different, but it's also based on entropy. But in the Avramov-Milchev, if you read their derivation, which is described in this reference here, they use the total entropy of the system. The total entropy is the sum of configurational entropy and vibrational entropy. It's a sum of 2 parts. For this derivation, the total entropy. For this one, just the configuration entropy. This is more related to the Adam-Gibbs equation. And there are many others. We cannot spend the whole course, here discussing viscosity models, but if you're doing a thesis, if you're really interested in viscosity, you have to study the derivations of all these equations. There are 10 other equations, but this is a very important one. If you look here in the number of citations, you understand that this is a very, very important viscosity model. And well, a key part here is to calculate configuration entropy. So one way to calculate the configuration entropy is by measuring the specific heat in a calorimeter. We have a calorimeter here. Many labs have a calorimeter. You can measure the specific heat of your system. If you are working with anorthite glass or Fresnoite glass or diopside glass or lithium disilicate, any glass that you have adopted for your exercise, your homework, and this is the second exercise actually that I'm giving. The first was to fit the viscosity curve, and now I'm challenging you to find the specific heat of the crystal as a function of temperature of the crystalline material, isochemical crystalline material. Then you have the specific heat of the glass. See the data points here? Specific heat of the glass is a little bit higher than the specific heat of the crystal because of the configurational contribution. It has a vibrational and a configurational contribution, and then you go to TG, there is a jump, because then you move from a frozen liquid to a supercooled liquid. There is a jump, more freedom in these molecules. And then maybe you even measure, the circles here mean measurement points, a little bit above TG. Again, you normally enter in a region where crystallization happens, so you can no longer measure the specific heat, but you can measure in the glass, through the glass transition, and a little bit here in the supercooled liquid. Now, you can also go above the melting point and measure the specific heat of the liquid, of the true liquid, and also a little bit here of the undercooled liquid before it crystallizes. Okay, in the end, experimental data points for the crystal, no problem. If you have a very good calorimeter, you can do from almost zero, this is 0 Kelvin, up to the melting point, then it melts. This is melting, jumping CP. Then you can measure the liquid in the glass, that supercooled liquid in the glass, and you have this curve here. Now, how you can calculate the configuration entropy? The configuration entropy as a function of a temperature is the configuration entropy at TG, this is TG, plus the integral of CP liquid, CP of the liquid, minus CP of the glass, divided by T, dt. This is an integral from TG to wherever temperature you want to calculate it. This is the configuration entropy. We have a problem here. Who can tell me what's the problem in trying to do this calculation? This calculation is very simple. It's just an integral, but there is a theoretical problem here. Looking at the figure and looking at the equation, what's the problem that we face if we try to do these calculations? And you will face this problem because this is the second homework, the second exercise for next week. You have to calculate the configuration and entropy of your glass.
The discontinuity that you have between the glass and the liquid?
Here, there is no data points, but we can fit. Here, there's no problem. We can fit a polynomial curve. The problem is here, right, David? There is no data for the glass because the glass only exists below TG. So you have also to fit a polynomial. You have these data points here. You have somewhere to extrapolate this curve here with a proper polynomial to be able to have this part here. And the same problem is here because the supercooled liquid no longer exists below TG. So we also have to extrapolate this curve down to here with a proper polynomial. So to get the Cp of liquid as a function of temperature, of course, in the whole range of the liquid and of the glass, you need to do two extrapolations, which are very tricky. Which equation are you going to use for here and for here? It's a polynomial equation, but there are several possibilities in this. Mathematically, it's very simple to do, but physically complicated because you have to find a proper way to extrapolate here and extrapolate here. But this is a nice exercise that I'm going to give to you. And you have 2 weeks to do this. So, I don't know, you have 1 week. Next week we have class, yeah. Configuration entropy. Any questions? This is a key problem in glass science. This is the fundamentals of the vitreous state or of the glass state. This is one very, very important. Okay, let's continue. Now, so the final solution, if you assume that the Cp of the liquid minus Cp of the glass can be expressed by a very simple equation, A plus Bt. It's almost, this is a straight line. This is the easiest assumption you can do. You can integrate A plus Bt, and the final solution is that log of viscosity is A6. Remember, A6 is just A to infinity. B6 is that A of the former equation, and this is the configuration entropy. Configuration entropy at Tg, this is a measured value, then A log over T over Tg plus B times T minus Tg. This equation results from this assumption here, that delta Cp is A plus Bt. The difference is given by A plus Bt. And A and B can be calculated from the calorimetric curves. It comes from the fit to the calorimetric curves. So, if you measure this by a calorimeter, then this equation 18 reduces to a two-parameter, unknown parameter, A6, B6, because all the others come indirectly from calorimetry. So a plot of log viscosity versus 1 over T S conf, this expression is S conf, requires only linear fitting, And nicely, this is a test of this equation. Plotting log of viscosity versus 1 over T S conf results in a very nice straight line from -1 to +15 or so. So those curves which were highly curved, the viscosity curves are highly curved, they become linear if we plot in this scale, as giving an indication that this Adam-Gibbs model works really well. Because S configuration has been measured independently by calorimetry. So we have only two parameters to fit, A6 and B6. So this is a test of this expression here. Okay? So you'll be calculating the configuration entropy for your glass. You just need calorimetric data. And then you fit the viscosity of your glass using this type of curve here. Log of viscosity versus 1 over T delta S. And it should give a straight line. So this is the third fit, because last week you have worked with a Vogel-Fulcher equation and with the LaMaV-CeRTEV equation. This is the third equation you're going to use to fit the viscosity of your glass, right? Second homework. Okay, I'm showing again this plot just to remind you that for the configuration entropy, we only need the CP of the liquid minus the CP of the glass. As we are not plotting the viscosity below Tg, we are only plotting the viscosity above Tg, we do not need to worry with this part here, okay? You only have to worry with this polynomial here and this one here, because you'll be calculating from Tg and above. So this will be the only problem, to extrapolate here and to interpolate here. Some glasses, like for instance B203 glass or albite glass, some glasses are very, very stable against crystallization. So for those type of super cool liquids, one can get data points even here. If they don't crystallize, you can get data points all the way here. But the glasses you are working with crystallize easily. I gave you on purpose glasses which crystallize easily because later on we are going to calculate nucleation rates, growth rates, and things like that. So you all have glasses which crystallize easily. So for your glasses, there will be no data points here. Okay? Now, here at LaMaV, we have tested 14 equations. I have shown only 5 so far, but there are 14. And I'm not going to discuss all of these equations with you, but the names are here. There are many, many names, and some of these work okay, others do not work okay. We performed a very rigorous statistical method called bootstrapping to check which one fits better data points for 35 oxide glass forming liquids. And we found so far that the LaMaV-CeRTEV, the Austin-Angels equation, the Demetrius equation, the Maegua-Vogel-Fulcher, and the Kivelson equation work really well. It's tough to distinguish between these equations in the range where viscosity can be easily measured from the liquidus to Tg. Just to show you some examples, and I have mentioned this before to you, these are some fits. I know some of you are working with lithium. Who got the lithium disilicate? Well, for lithium disilicate, you see there's data points here, data points here. Both equations fit very well, I think. It's hard to distinguish one from the other. I hope you find, yeah, you found this result we are going to discuss. So this is the response. This is for the homework I gave you. And lithium diborate, is somebody working with lithium diborate? No. But for lithium diborate, the same. You know, data points here, and these two equations fit very well. Now, just to remind you, so what happens during viscous flow in an atomic scale? In an atomic scale, we have already mentioned that cooperative rearrangements, because this is a viscous liquid. Here, in water, there's likely no cooperative rearrangements. Each water molecule moves almost independently of each other. But in a very dense viscous liquid, there must be some sort of cooperative rearrangements of whatever structural entities your glass has. And this leads to a non-Arrhenian temperature dependence above Tg. By non-Arrhenian, I mean curved. That's why the viscosity plots are curved. If you plot log viscosity versus 1 over T, they're curved. They're non-Arrhenian. Only at the so-called fictive temperature, I'm going to explain this in a minute, then below that, then isostructural viscosity takes over. This is the equilibrium viscosity, and measurements are normally done here. Highly non-Arrhenian, then it becomes Arrhenian because the structure of glass, of the liquid, is frozen, and then isostructural viscosity takes over. So it's non-Arrhenian above Tg. However, in the glass transition range, viscosity becomes time-dependent as the time scale of structural relaxation exceeds the time scales of the deformation process for measurement. This leads to isostructural viscosity. So below the fictive temperature, which may or may not be coincident with Tg, becomes isostructure. In the relaxation process we are going to talk next week refers to relaxation from here to here. This is the relaxation process that takes place below Tf or Tg. The glass starts with isostructural viscosity. If you wait some time, the viscosity will move here. If you wait longer, it will move here. Wait longer, it will move until it reaches the equilibrium viscosity curve, which is extrapolated from the equilibrium viscosity data points that we measure. That's why it's very important to know which equation we have to use, because as I told you, the Vogel-Fulcher-Tillman will lead this to infinity, and other equations will lead to other values. So it's still an open problem. It's an open problem. Which equation can be used to extrapolate the viscosity below the Tg or the fictive temperature? It's not clear yet. There's discussion in the literature. Now, before I proceed, and since I mentioned the existence of this fictive temperature, I'm going to just briefly mention the meaning of fictive temperature. And for that, I think it's let me go back to some slides, to the first slide. Here. Well, okay. I have a liquid, supercool liquid. For a given cooling rate, glass transition takes place. Now, if we do a faster cooling rate, much faster cooling rate, glass transition could take place here. This is the fictive temperature. This is another fictive temperature. It's the temperature where the structure of the liquid was frozen for that particular method of making the glass or for that particular cooling rate. So what's the difference between the fictive temperature and Tg? Sometimes they are the same, sometimes they are not the same. The difference is if we plot the same kind of plot here, okay, one glass was made with a very slow cooling rate, another sister glass was made with a high cooling rate, 1 and 2. Cooling rate here is higher than here. Fictive temperature 1, so TF 1, and here TF 2. Okay, now we have this glass 2 here at room temperature, this glass here at room temperature. Now what happens if I take this glass here and heat it up in a DSC or in a dilatometer? It will go, and will relax. This is the Tg. The Tg of this glass is much lower than the fictive temperature of this glass, because it comes to that range of 10 to the 12 pascals second, and then we relax back to this point, and that's the Tg that we measure. Tg is something that we measure. It depends also on how fast or how slow we measure, but it's not the same as TF. Maybe by coincidence, if we come with this glass here, the cooling rate was such that by coincidence, well, the Tg is about the same. So Tg may or may not be the same as the fictive temperature. And this is the name, fictive temperature. It was invented by a researcher called Tu, many years ago in the 20s. Okay, let's go back. So I was talking about then isostructure of viscosity. So the supercooled liquid is frozen. As I explained last week, frozen means only a temporary state. So a glass is a rigid material, is not a solid, which is frozen. But we can unfreeze a glass by heating it. And we will relax and goes to the equilibrium viscosity. So the curve that we have here at high temperatures, above Tg, is always the equilibrium viscosity, because the liquid had time enough to relax during the measurement. It becomes non-equilibrium, so iso or non-equilibrium viscosity below the fictive temperature of the material. All right. So this is a plot for soda lime silica glasses. If you have been working with glasses, you know that soda lime silica glasses are the most popular type of glasses. This type of glasses here, soda lime silica glasses. They're very good glasses and they're inexpensive. And they have good chemical properties. You can easily make them. That's why they're so popular for glass windows or bottles or many other type of products. And soda lime silica glass, this data here from maybe 50 different authors. Each company makes their own recipe with more alumina, less alumina, more potash, more sodium, less sodium, more calcium, less calcium. The viscosity varies. If you look at this as a log scale, say by 1 order, this is the size of 1 order of magnitude. This is about 1 order of magnitude from one composition to the other, changing a little bit here and there. And then, you know, equilibrium, isostructural. Some people are able to measure the viscosity below the fictive temperature and then isostructural viscosity. Also interesting, the effect of water. Most glasses have a little bit of OH. When you make the glass in the lab, there is humidity and so on, a little bit of OH groups from the atmosphere. 20 ppm, 100 ppm. Some minerals have a lot of water, 1–2% of water, because their synthesis of these minerals in nature is under pressure, you know, with high humidity and so on. They may have a lot of water. Water has a huge effect on viscosity. So these are soda lime silica glasses with different amounts of water. The viscosity decreases by many orders of magnitude. There's always some water. And if you're going to do a thesis in the end, like Mina and Maziar, who are developing new glasses, people who are developing new glasses, when you come up with a good glass that you say, this is the one I'm going to characterize for my thesis, you have to measure the amount of water by infrared. You know, you can have a nice peaks in the infrared spectrum and see how much water your glass has. Because if you don't measure this, you're not able to reproduce this glass. If you produce a glass in Arizona, a very, very low humidity, and a glass here in Brazil in summer with very high humidity, they'll probably have different amounts of water. Even if exactly the same chemicals are used, these two glasses will be different. Different regarding dynamic properties, viscous flow, diffusion, nucleation rates, crystal growth rates. It doesn't have a large effect on mechanical properties. If you're going to measure the mechanical properties, a little bit more or less of water makes no difference. Or the density of the glass, or even the refractive index, these differences are negligible. But for dynamic properties, this is very important. I'm saying this because not many people realize that glasses have water and how important this component is. Now, I was talking about fragility. Remember, in those equations, we had 3 unknown parameters. Eta infinity, which is more or less known. Tg, which you can measure independently of viscosity. And M. M is the fragility, is this quantity here. M is the derivative of the viscosity. This is the viscosity curve. The scale is Tg over T. If you plot in this scale Tg over T, you can group All these glasses together is a normalized plot. It's a normalized viscosity plot scaled by Tg. And the fragility is the derivative calculated exactly here. 1 means T is equal to Tg. So you calculate the derivative here. See 12. This is our 12 is our Tg. Here we have to calculate the derivative. This is M, the fragility of the glass. So some glasses are very fragile. M is very high. Other glasses are strong. The slope is smaller. The fragility for different glasses, you can see here, varies from about 17 to 200. These are very fragile glasses. These are strong glasses. Pure silica, pure GeO2. Diopside, Paulo, that you work with diopside, the fragility of diopside is about 60. The fragility of lithium disilicate is about 45, will be here. And so on. Polymer glasses have very low fragility. Oxide glasses, the maximum I have ever seen is about 100. Up to 100 for oxide glasses. Metallic glasses also tend to be fragile, and the fragilities go from 40 to 80 or so, more or less, right? So you can now calculate the fragility of your glasses. You have your glass, you have the viscosity curves, so you can calculate what's the fragility of your glasses. Another exercise. See, it's summing up. Just calculate the derivative there. Or fit, or you can fit the equations using the other forms that I gave today. You just fit in that form, the fragility comes automatically. Right? There's a lot of information I'm passing to you. This is my postdoc Daniel Casar did very nicely for a series of glasses, like GeO2 glasses, very strong. Anything below 25 or so is very, very strong. And the weakest or most fragile glass that we have tested is strontium borate, fragility of 90. Fragility of 90. There's a whole, you don't have to copy all this, but lithium disilicate is here. This is lithium disilicate, 44 or 45. This, of course, depends on which equation you use. If you use the Vogel-Fulcher equation to fit, you have a higher fragility because the Vogel-Fulcher, it's steeper here than the Avramov-Milchev. I bet that if you fit with the Avramov-Milchev, you have a somewhat smaller, not a lot smaller, but somewhat smaller value of fragility. Diopside is here, 60. Anortite, who has anortite? Anortite glasses, Deborah's glass, about 55 or so. Fresnoite, this is very fragile. Who is working with Fresnoite glass? Nobody? Which glass you have, Elena? Metasilicate. Nobody has Fresnoite glass. Which glass you have? 1, 2, 3. Okay. 1, 2, 3. 1, 2, 3. No, this is this one. 45. More or less. So you can check your results. Okay, so these are the equations.
Excuse me. Is there any physical meaning for the fragility index?
Yes, the meaning is that the structure changes a lot with temperature. If you have a strong glass, a strong glass, so I was asking Maziar, the difference between a strong and fragile liquid, what's the physical meaning? The physical meaning is that for a strong liquid, the molecular structure does not change with temperature. It's Arrhenian. For a fragile liquid, see the apparent activation energy, see this is the apparent activation energy, increases, 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 so it changes much more with temperature. This is the easiest way of distinguishing a fragile from a strong liquid. How much the structure changes. Now, remember I told you, oh, here we have 13 viscosity equations fitting to a fragile and strong liquid. Taking this fragile liquid here, look at the difference between the different equations. Some equations are really bad. Look at here, this blue one. Other fit okay for at some range, but not always. So this is the kind of test that we did to distinguish those 14 equations. And some fit very well, all liquids. Others fit well, strong liquids. See, for this strong liquid, most equations, except for the blue one, fit the data quite well. But once the viscosity starts to change a lot for fragile liquids, some of the equations are much better than others. This is just an overall picture. We have done this for different fragilities, different classes, but this gives the major difference. So, effects of composition. So there's strong, fragile liquids. There's also the so-called hard, really covalent, predominantly covalent bonded liquids. The covalent and metallic liquids can be called strong, whereas the pure ionic or van der Waals organic liquids are soft. So this is another type of this distinction between glass-forming liquids, hard and soft. Hard and soft. You can see in details in the book chapter. Then, effects of composition. We have, just to give you an example, pure silica. 0 means pure silica glass. Adding a little bit of sodium oxide. See how much the T12, this is the TG, the temperature where the viscosity is 10 to the 12 Pascal second. See how much it drops. A few percent sodium or lithium or potassium, rubidium, these so-called modifying elements drop a lot the viscosity. And then there is a region of liquid-liquid phase separation. We are going to talk about liquid-liquid phase separation in a few weeks. This is an important phenomenon. Things are messed up. You see, the things are messed up. In a few weeks I'm going to explain why there is a complex behavior of viscosity and of many other properties within this range where two liquid phases coexist. And then again, this normal behavior of just decreasing the viscosity with the amount of modifier oxide added. But the key feature here is, let's forget the complications about liquid phase separation for the time being, but look at how much it changes here and how much it changes here. Why is that? Why the viscosity changes dramatically here and very monotonically in a very boring way here? Why?
Because of broken of the linkage of silica.
Yeah, but here I'm breaking also. Every atom that you add, I'm producing non-bridging oxygens. What's your idea, Benjamin?
You said you had a traffic jam, like all these whatever is diffusing in the melt is competing with one another, so you can't go any faster than the next car.
Yeah, here I had a traffic jam. I had that three-dimensional structure. All the corners, like for pure silica, all the four corners are shared with other tetrahedra. Now, when I add, each sodium atom breaks one bond. So you have a huge effect. This is the scissors effect. You heard of the scissors effect. You have a chain, very strong chain. If you cut one link, that's it. So here, we're cutting links of this very strong thing, and we are unjamming the process. Here, it's already completely broken. You know, 1 or 2 atoms more, 10% more, it makes almost no difference. This is very interesting. And we have to realize this. And that's why it's very difficult to reproduce pure silica glasses. Pure silica or pure Germania or pure P2O5 or pure TeO2 or pure BeO3, pure oxide glasses are extremely difficult to reproduce. Every time you make one, you come up with a different properties because every glass has small amounts of this, a small amount of that, small amount of different elements. It's a huge effect with very small quantities of this element and also of water. Now, if the glass is already broken, the structure is already broken, we are going to talk about glass structure in a few weeks, and you see exactly what happens. So this is a striking plot, and I like very much this plot because it shows the nature of the glassy state. Now, we are talking about silica glass. Now, if we go to borate glasses, this is borate glasses. 0 means pure B2O3 glass, and then adding the same sodium oxide. Now the viscosity increases. See? This is T12, where the viscosity is 12. 10 means the viscosity is 10 to the 10 Pascal second, and so on. But let's take this one, the TG. The TG increases. I'm adding sodium oxide, and the TG increases, and then becomes monotonic. But why the TG increases? It's the opposite effect. In silicates, the viscosity, TG, or any property related to viscosity decreases. Why it increases here for borates?
Because the glass forming ability decreases and we need the fastest cooling rate. So we need to freeze the structure at high temperature.
No, but I mean for the same cooling rate, for different glasses produced in exactly the same way. They are produced exactly the same way, but with 5, 10, 15% of sodium. The Baurel anomaly, this is very important. The Baurel anomaly, Graziella, you remembered from Oscar's classes, I think. Boron oxide changes the coordination from 4 to 3. Well, it's the opposite. The pure boron oxide has a coordination of 3. It's BO3. It's a boron atom surrounded by 3 oxygens. When we add sodium, it changes to 4. And then the viscosity increases. It changes to 4. This is well known using NMR data. People measure the amount of boron 3 and boron 4, and it's well known that the boron 4 increases with any alkali that you add, so the viscosity increases until about 25% is reached, and then the fraction of boron 3 and boron 4 does not change any longer, and you have a monotonic effect. But only with boron oxide. With all the other glass-forming oxides, germanium oxide, tellurium oxide, phosphorus oxide, and silicon oxide, when you add alkalis, the viscosity decreases. A lot in the beginning, and then in a very boring, monotonic way after 20 or 25% molar of the oxide is added, because the structure is already completely broken. So to summarize, this plot shows the effect of T12, is always the TG here, for different oxides added in metaphosphate melts in this case. Metaphosphate is P2O5, P2O5 dot some oxide. 1 mole of this, 1 mole of some oxide that is added to this glass-forming P2O5. See, lithium, sodium, potassium, rubidium in the periodic table, decreasing the TG or decreasing the viscosity. Then we have magnesium, calcium, strontium, barium. The oxides with valence 2. And now with valence 3, aluminum, ytterbium, erbium, chromium, etc., praseodymium, and others. So you can control the viscosity of glasses by adding one or the other element. And this is what Graziella is trying to find out now. She's doing a thesis trying to find exactly the effect of different elements in several properties of glasses. You see how organized these kind of properties are, and you can almost predict the effect of certain elements on the properties if you know the size. This is the size, this is the valence of the element divided by the distance between the element and the oxygen, the field strength. This is a measure of the field strength, but it varies monotonically. You can more or less predict. So if you want a glass, a metaphosphate glass with high viscosity, add alumina. If for some instance you want to increase the viscosity, add alumina or iron 3, Fe2O3. If you want one with a very low viscosity, rubidium. Okay? And this can be done for other glass formats. This is a particular example for this kind of binary composition here, but similar plots exist for other systems. This is an interesting one, the effect of alumina on sodium silicates. This is a silicate. There are silicates, albite, jadeite, nepheline. There are silicates containing alumina and sodium in this particular case. Alumina, see, this is T11, almost TG, a little bit above TG. In the different compositions, see, alumina increases a lot the viscosity. You see, it goes here, the TG from 800 or so to 1200, almost 1200. And it peaks exactly when the ratio aluminum divided by sodium aluminum is 0.5. We are going to explain this in the structure class. You see why this happens. These changes are related to structural changes in the liquid when certain oxides are added. Alumina is a special one which has this behavior, and even for T3, this is T3, this is T11, you see the peak of viscosity when this ratio is exactly 0.5. Aluminum divided by sodium plus aluminum. Water. I have already told you the effect of water is terrible. Well, it could be welcome if you want to decrease the viscosity of a glass, but it's very strong. So these are silicates, you know, silicate systems, different silicate systems with different contents of water. You see, in the beginning, it doesn't change much until 0.01% or so. 0.01, these are very, very small quantities, very, very, very small quantities. And then, you know, starting more or less here, 0.005 or so, this is 0.1, so starting here, 0.005, a very, very strong effect of water. So this is the TG divided by the TG of the same glass containing almost no water. TG of a glass with water divided by the TG of a dry glass. So you can have a little bit, small amounts of water after a certain critical ratio, which is 0.005 or so. So if the viscosity decreases, then the diffusion rates, the relaxation rates, the nucleation rates increase, the crystal growth rates increase, the glass forming ability decreases. It has a strong effect. I think metallic glasses do not suffer from this effect here, but they suffer from another effect. They may oxidize a little bit. When you're trying to produce a metallic glass, certain amounts of oxides are formed which have induced complications, but no water as far as I know in metallic melts. I'm almost finishing, just to give you how much impurities can affect the viscosity of glass. Once Marcio was a former student of mine trying to understand the viscosity of silica. This is pure silica. I mean, there's no such a thing as 100% pure. But this is a silica glass, but it has a little bit of sodium, a little bit of iron, a little bit of alumina, a little bit of water. And there are 4 or 5 types of silica. This is one type which is made by melting quartz crystal. You can get very pure quartz crystals and melt. So you have a silica glass. Look how much oh, it's a strong glass. It's a strong glass. So it's Arrhenian. This is not curved. They're Arrhenian curves, plots, which is nice. But how much it varies from altar to altar. If you look here, this is 2 or more orders of magnitude. Two or more orders of magnitude. This is 100 times. Just changing tiny amounts of whatever impurities the material has. And the effect is larger here, close to TG. This is TG, right? 10 to the 12 is TG, than here at the liquidus. So the effect at the liquidus is not so intense. It's like if these curves are more or less like this. See, more impurities, less impurities. The difference here is 2.5 orders of magnitude. Here is only 1 or 2 times. If you do the same plot for soda lime silica glasses, and I have shown this before, then the effect is not so great. The variation in composition of this soda lime silica glass is much larger than the variation of pure silica glass. But the effect is not so large. It's 1 order of magnitude or so, taking the data from different authors, changing a lot, because these classes are already full of non-bridging oxygens. Their structure is already broken a lot. So this is just to compare pure silica glass with an already broken structure glass such as soda lime silica glass. Finally, just to finish this class, viscosity of glass ceramics. Now, some people here are working with glass ceramics. Glass ceramics are more complicated because in the microstructure, one has a glass phase with crystals embedded in the glass ceramics. And these crystals may have a small, an average, or very large volume fraction. So these are composites. What's the viscosity of a composite? Because the crystals are rigid. The crystals do not flow. Only the glass phase flows. So there are models here. There are models, that allow us to estimate the relative viscosity as a function of the volume fraction of the crystals. Rigid solid inclusions crystals, and also depends on the morphology, if they are spherical, if they are plate-shaped, if they are needles. So there are equations, and there are several equations that allow you to calculate the viscosity as a function of the shape of the materials, for needles, for spheres, in the volume fraction. So this is the volume fraction. The viscosity obviously increases. The viscosity of a glass ceramic is higher than the viscosity of that glass phase without crystals. And you can calculate this. Now, instead of crystals, one may have bubbles. Glasses have bubbles. Bubbles have no resistance to flow. Now, if you have bubbles, then the viscosity decreases. And there are equations, several equations here. So, you can measure and then fit or calculate the viscosity of pure glasses, but you can also do so for glasses containing crystals, which we call glass ceramics, or for glasses containing bubbles. Right? Final transparency, and this is very nice. Glasses are like solutions. They're frozen liquids, and they're solutions of many ions. There's no microstructure. Now, I'm not talking about glass ceramic now. Pure glasses. They have no microstructure. So in principle, one can calculate the viscosity and many other properties if you know the chemical composition. And there are equations, and there are databases, software like SciGlass or Interglad, which allow researchers to estimate the viscosity by knowing the chemical composition. So with this, we finish the topic viscous flow in glasses. And next week, we will be talking about relaxation, glass relaxation, okay? Is there any question?
I have a question.
Yes.
It's not about this, but it's about the fictive temperature and TG.
Okay.
I was asking myself, how to measure the fictive temperature when it's different from TG, since you
there are ways to measure the fictive temperature. There's a very nice method produced by Connie Monahan, where you can, for instance, pull a fiber, quench a glass very fast, and then cast a very large piece of the same glass in a mold, which you have a much lower cooling rate, so they must have a very different fictive temperatures. Then you can heat them up, and by the shape of the, I can give you the reference later on because I don't have it here, but the shape of the TG curves will be different. The shape of the TG curves will be different, and from the area under these curves, you can estimate the fictive temperature, because they will relax at different pace. Although the TGs will be similar, maybe 5 degrees Celsius or so, 10 degrees maximum difference, but from the shape of the relaxation curve, which is indirectly reflected in the DSE, you can estimate the fictive temperature. I can give you the full reference later on. We have done this in our lab. And I think, Paulo, you had a question when I was erasing the blackboard.
We can think about the property, toughness of the material.
Yes.
Related to fragility.
Yes, that was a good question. Paulo was asking if the fragility concept can be related to the strength of the glass or with the toughness of the glass. No, this is a bad word because people immediately relate fragility to mechanical properties. This has nothing to do with mechanical properties. It's the liquid fragility. That's why I made my best to emphasize that it's the liquid fragility. It's just confusing words. No relation to the mechanical properties. No obvious relation anyway. You can think that, okay, a very, very fragile glass has a lot of broken bones and maybe it's not so strong as strong in the mechanical sense as a strong glass. But the meaning of this fragility is just how much the viscosity curve departs from an Arrhenian curve. Okay? Graziella.
The physical meaning of fictive temperature is like you cool it much more faster than to achieve the TG. So like something like that.
The fictive temperature is just the temperature where the structure was frozen. So the glass remembers that. The glasses remember their thermal history. They remember the thermal history. You see next week, we'll talk about relaxation processes. And the speed of relaxation depends on the fictive temperature. So it's very interesting because the relaxation times, tau, next week we are going to see, they depend upon the actual temperature that we are studying and also on the fictive temperature of the glass. So glasses are interesting. They remember, they memorize their thermal history.
Because when we say TG, we say it depends on the cooling rate, right? But in fact, the fictive temperature depends on
the fictive temperature depends on the cooling rate. The TG, you normally measure by heating. You measure by heating. So you erase the cooling rate story, more or less, but not completely. As I told you here, the shape will bring retain some information from the cooling path. From the shape in these areas, you can estimate the fictive temperature. Paulo.
I don't know why the lower the TG, the higher is the viscosity. When I added metal oxide, I can't explain it. How can we explain it?
No.
The lower the TG, the higher is the...
No. The lower the TG, the smaller the viscosity.
The smaller?
Yeah. Did I say otherwise? No. The lower the TG, the lower the viscosity. If I said otherwise, I messed up. But smaller TGs, in general, is smaller viscosities because you know you can plot like a curve here. This is TG, 10 to the 12 Pascal second. If this is log of viscosity, so for this glass, the TG is here. So this is the TG of this glass. And for this glass here, the TG is here. So this has a higher viscosity and TG is higher.
If we add aluminum oxide to pure silicate, we will lower the TG.
In the beginning, yes. If you add anything to pure silica in the beginning, you lower the viscosity. And then maybe it reaches some maximum. I don't have the actual viscosity curve for a pure silica alumina system, but my guess is that in the beginning we will lower, at some stage we will catch up, but the effect is more, the effect of lowering viscosity is much more easy to see when you add the so-called modifier elements. Sodium, lithium, potassium, calcium, magnesium. These guys almost always decrease the viscosity, except for the borate glasses because of the Baurel anomaly. Yeah? Okay, thank you very much. See you next week. Bye-bye.